Is there a presentation mode? Does anyone know if there's a presentation mode that I can display? Might be page view. We just best zooming in. Yeah.
They can just upload the report.
Hi, everybody. So I'm going to talk about using some geometric ideas and a little bit of algebra to find rational solutions of polynomials. You might think solutions of polynomials are very easy. But that's polynomials in one variable. We're going to talk about polynomials mostly in two variables. But let's start off with a simple example. So does this equation x squared plus y squared equals z squared have integer solutions? If you're on Zoom, you could type into the chat if you can see any integer solutions. Anybody in the room can tell me any integer solutions? Yeah.
4 and 5.
Okay, 3, 4, and 5. Very famous. Yes, this equation is related to right angle triangles, of course. Anybody? Are there any more solutions in integers?
5, 12, 13.
5, 12, and 13. Okay, so there's lots of them, and there's some famous formula that gives them all. 1, 0, and 1 is actually the simplest one in a sense, if one was just looked at this and didn't know anything clever. So what I want to do is say, can we find all the infinitely many solutions of this by some geometric process? To do that, I'm going to change things a little bit. Instead of looking at x squared plus y squared equals z squared, let's look at x squared plus y squared equals 1. So does this have integer solutions? Yes, it has 1s and 0s. And minus 1s and 0s. So there's 4 integer solutions that you could fairly easily see. These are all the integer solutions. But if instead of looking at integer solutions, if we ask about rational solutions, then we get back to the previous question. So does this have any rational solutions? Yes, it has lots of them. So it has the 1, 0s that we've seen before. It also has things like 3/5 and 4/5. You can just take your Pythagorean triples and divide everything through by z, and you get a solution to this equation, x squared plus y squared equals 1. So rational points on the circle. And if you know there are lots of Pythagorean triples, then you know there are lots of these. So how about we find these if we didn't already know that they existed? So what we can do, we can start off with one point that we know of. Let's pick minus 1, 0. Draw a line through it with a gradient of q. And this line is going to intersect the circle in one other point. Unless we choose the tangent. We just not do that. And then we can calculate the coordinate of this point here. So we'll calculate the xy coordinate of the second intersection point. Okay, so while we do that, we write down the equation of the line is y equals q times x plus 1. We substitute that into the equation of the circle. and we get x squared plus b squared times x plus 1 squared equals 1. Then we can rearrange this into, it's a quadratic equation for x. So we get this quadratic in x. We're treating q as something that we fixed here. So how about we solve this quadratic equation? What methods would people use to solve this quadratic equation? The formula. Okay, great. So we can use the formula. There'll be a bit of a long calculation. There'll be some horrible square root in it. If we do the calculation, we magically find that this big expression that we're taking the square root of is actually the square of a smaller expression. So the square root goes away. Would anybody solve this quadratic by a different method? So you could, are you thinking of completing the square? There's certainly ways you can do it like that. I think in this case, we do something extra about this quadratic. We already know that this line goes through the point minus 1, 0. So we know that minus 1 is a root of the quadratic. And therefore, we can factorize it. We pull out this factor of x plus 1 that comes from the root we already know about. And we get some other factor. And the benefit of doing it this way is we see that everything is going to be rational here. So we're assuming that q is a rational number. I should have said that. And then because we've factorized out this x plus 1, what's left has to be rational. So this avoids going through the square root, doing a long calculation and discovering that by some magic coincidence, the thing you're taking the square root of is a square. This automatically gives you another rational point. So we get the value of x is this expression here. When q is rational, this is a rational number. And then you can substitute that back in and work out the value of y as well. So we can draw any line through this starting point with a rational gradient, and we get a whole lot of rational points on the circle. And you can check fairly easily that this method actually gives you all the rational points on the circle. It's because the line you draw through them would have to have a rational gradient. So if you do the formula for Pythagorean triples, or if you've seen a formula for Pythagorean triples, this method actually gives you back that formula. If you write q equals m over n, where m and n are integers, and then you substitute that into these formulas for x and y and clear out the denominators, you end up getting the standard formula for Pythagorean triples, which you sort of might have discovered by some long algebraic process that isn't always terribly motivated. Here's a geometric trick that gives it to you very quickly. Okay. That's one thing we can do with this unit circle. What if we look at a different circle? So what if we look at x squared plus y squared equals 2? Does this have rational solutions? Anybody think this has a rational solution? I'm seeing some nods. Do you think? 1, 1. Okay. So of course, the point where it crosses the axis, this is now minus root 2 and 0. So this isn't rational, but there's a rational point at 1, 1. There we are, and indeed 4 of them with all the negatives as well. And we can do the same thing. So we can draw a line through one of these rational points with a rational gradient, look for the other point where it intersects the circle. That'll give us a quadratic equation with rational coefficients, and we already know one root of it because we already know one intersection point. Therefore, we can factorize and get a second rational point of intersection. And this will work for any circle or any equation in x and y of degree 2, so long as it has a rational point to start off with. we'll always then get infinitely. There might be ones that have no rational points at all, which is a slightly different sort of question. But as long as there's one, this method gives us a parameterization of infinitely many rational points on that curve. Okay, so that was degree 2. Degree 1, of course, is easier. Degree 1 is just a line. What about degree 3 equations? So does this equation, y squared equals x cubed minus x plus 1, have any rational solutions? Yeah, what do you think?
0, 1.
0, 1. Okay, great. So I picked this curve because it has some rational solutions that are easy to spot. Anybody see any more?
1,
1, 1. Okay. Yeah. So this curve actually has 6 easy to spot rational solutions. 0, 1, 1, 1, minus 1, 1, and their counterparts down below the y-axis. Does it have any more? This is a much harder question. So we might try and do the same thing as we did before. Draw a line through one of these points that we found. Where else does it intersect the curve? It intersects the curve now in 2 other points. And to find the equation, to find the coordinates of these points, we'll be solving a cubic equation. We know one root of that because it goes through one point that we chose. We can factor out a factor coming from that root, and we're left with a quadratic equation, which has rational coefficients, but we don't know anything else about it. So when we try and solve this quadratic equation, we'll have to use the formula. We'll get a square root. We probably won't find more rational points. So the same method exactly doesn't work, but we can tweak things a little bit. We can draw a line that goes through 2 of the points we already know about. So I picked -1, -1, and 0, 1 are 2 points we already know about. This line is actually going to intersect the curve somewhere way up there, because this curve is getting steeper and steeper. So if I zoom out a bit, we can see the other intersection up here. And we can do the same sort of process. So we can write down the equation of this line, solve to find these 3 points. It'll be a cubic equation, 2 of the roots. So we can factor out both of those 2 things, and we're left with a linear equation for the 3rd root, which will all be rational again. So I actually did this for this example. This particular line is y equals 2x plus 1. We substituted in the equation of the cubic, the curve. We get this cubic equation for x. I rearrange it like this. And I know that this cubic has roots x equals -1 and x equals 0. So I can factor those out. And I get x plus 1 times x minus 5. So there's this 3rd point of intersection has x equals 5. And then I can plug that back into the equation of the line and get y is 11. Which, if you check, this is a solution of this cubic. Something that would have been a bit more work to find by hand. Obviously, a computer could have found this very quickly. But this sort of says we could start off with a few points that were really easy to spot and find some slightly bigger ones. And potentially, we could find some much bigger ones that really would be hard for a computer to spot. So we can, maybe I should say, we could repeat this process. We've got a new rational point here, so we can start drawing a line between this new point and the ones we already had. So we might draw the line from 511 down to this point here, and it'll intersect the curve in another new point. That one there, I think, is 3 and 5. These don't necessarily, it's sort of quite lucky that this one has a lot that are actually integers. Generally, this process will end up giving you rational numbers with horribly big denominators. But what we could do then is basically, we get a new point, you could then repeat the process, drawing lines through various things we already know about, get another new point, and so on and so on and so on. So we don't, in the circle example, we could see all the rational points at once, because we could just change the gradient, we had the simple formula. Here we sort of generate them just one at a time, by having to wind our way through this process. But the coordinates do get big, either in size or in denominator very quickly. So this does tend to give us things that we couldn't have found just by brute force computer search. And there was nothing special about y squared equals x cubed minus x plus 1. I could do this with any cubic curve, just the same. So if I have 2 points already, I draw the line through them, I get a third point where it intersects the curve. So I said we could repeat the process and get more and more new points. We don't always get more and more new points. In principle, when you repeat the process, we might just rediscover points that we already had. So in this particular example of y squared equals x cubed plus 1, I believe there's 5 rational points on this curve. There's these 3 here, and then there's the reflections of this one and that one. And there's no more. If you draw all the lines, sort of every combination of lines between those points, you only ever rediscover ones you already had. So sometimes you get infinitely many, sometimes you don't. So if we want to try and understand when does it give us infinitely many, what's actually going on here, we can turn this into a group operation, where you take 2 points, you get a third. So it's slightly more complicated than what we just did. It's not just p plus q equals r, because that's very badly not an associative operation. It turns out that what you do is you take p plus q, you get r, and then you reflect it to p plus q. And this is associative. That's not a particularly easy thing to prove still. It's quite a lot of, well, you could do it by really brute force algebra in principle. There are better geometric techniques, but they're much more sophisticated geometry than just drawing lines and intersecting things. So we just believe it, but this turns out to be an associative operation. And therefore we get a group where we can add 2 points and produce a third one. And this group is a finitely generated abelian group. This is a theorem that was proved by Louis Bourdelle here in Manchester in 1922. So abelian group, because, well, the process we did, you draw a line through 2 points. It doesn't matter whether you're doing p plus q or q plus p to do that. The finitely generated bit essentially says there's a set of finitely many points that we can start off with and then do this process, and you'll end up getting all the rational points. This doesn't tell you how to find a finite set of points to start off with. It just theoretically says there exists a finite set for any elliptic curve that you can start off with and produce all the points. So one of the basic theorems of group theory, the fundamental theorem of finitely generated abelian groups, tells us any finitely generated abelian group is isomorphic to a direct product of z to the r times a finite group for some integer r. So this number r here sort of measures, in some sense, how infinite the group is. So if r was 0, you just have a finite group. If r was 1, that means you've got a finite group plus some other stuff that's just generated by one thing. And then if r is bigger, that's counting how many extra points you need to generate the whole thing. Sort of the finite group part we largely ignore. It sort of doesn't contribute very much to this infinite thing. But this number r, it's called the rank of the elliptic curve, and tells us, ignoring some finite thing, how many points do we need to generate everything. So the examples that we saw before, y squared equals x cubed minus x plus 1, turns out to have rank 1. So the points that we'd started off drawing, going 5, 11, and 3, 5 and things, if you keep going, you do indeed get infinitely many points by that process. But that's all. There's no other point that isn't coming from the ones we had there. Whereas y squared equals x cubed plus 1 has rank 0, I said there was only finitely many points, and then you wouldn't get any more. There are examples of higher rank, but they're harder to write down. And actually calculating what the rank is a hard process. Indeed, there's not any known algorithm that's guaranteed to tell you what the rank is of an elliptic curve. There's algorithms that give you an upper bound. You can try and get a lower bound just by searching for points. But in principle, these might never reach the same answer at the end.
Is that Pythagorean?
Okay. Right, yes. So I was saying there's curves of higher rank than these examples of 0 and 1. And I think in the 1930s, people really started to try and look for these. These are obviously pretty hard to find sort of things this big and complicated with the technology of the 1930s. They probably have some kind of mechanical calculator. But 1945, they got to rank 4, and this was sort of the biggest they could get. People were wondering, can you have arbitrarily large ranks of elliptic curves? But it sort of got stuck. Nobody found a bigger one than rank 4 for about 30 years. So people began to believe, maybe that's it. Maybe rank 4 is as big as you can get. Until the 1970s, when they started using electronic computers, that you could do a much more efficient search for curves of big rank, and somebody found a curve of rank 6. After that, you plug it into more and more powerful computers, and people found curves of bigger and bigger ranks. So all through the 70s, the 80s, into the 90s, the ranks were going up and up, and as you can see, the sizes of the coefficients become pretty enormous. This carried on until about 2000, when we got up to rank 24, I think, and then it stopped. People continued using big computers to search for these things, but they stopped finding higher rank elliptic curves. With one exception, 2008, Noah Melke's found an elliptic curve with rank at least 28. It's hard, as I said before, it's hard to say exactly, but at least we know it's bigger than or equal to 28, quite likely equal. And the numbers here, I apologize if you can't read these numbers. I had to make the font size very small so they fit on the slide. But this seems to be an exception, a special exceptional curve. Other than this, we don't know any examples of elliptic curves with rank bigger than 24, even given another 13 years of looking. So opinions have gone back and forth over time. Today, it's looking maybe like there's a bound on the rank of elliptic curves, that we're never going to get more than 28. There's theoretical reasons sort of both ways as well. In the 90s, people discovered theorems that suggested that there should be unbounded rank. Today, there's sort of heuristic models that suggest there should be a bound on the rank, and it is probably not much bigger than 20. So this is sort of makes it quite likely that this 28 really is the maximum there is. Okay, so these are things that people have been searching for. What about unsolved questions? So are there elliptic curves with arbitrarily large rank? As I've been saying already, is unsolved. I also mentioned the question of is there an algorithm that will calculate the rank of an elliptic curve? So this is connected to what's called the Bertrand-Swinnerton Direct Conjecture, which is one of the Clay Millennium problems that were written down in 2000 as major unsolved problems in mathematics. This is all talking about the rank. I said there was this finite group part, and that's much better understood. We know that the finite group part has size up to 16, and we know how you can find it exactly. But this rank part remains pretty mysterious as to how to understand it in general. You might ask me, what about curves of degree bigger than 3? So we talked about degrees 1, well, we talked about degree 2. There's an easy process that once you get a point, there are infinitely many. We talked about degree 3. Sometimes there's finitely many rational points. Sometimes there's infinitely many. Degree 4 and higher, it turns out there's only ever finitely many rational points. So these sorts of methods are never going to work for degree 4, because even if you had 2 points, you draw a line through them, it has 2 more intersections with the curve, you're still solving a quadratic. And there's nothing you can do. If you try and take 3 points, there's sort of no way to combine those 3 points into a line and find an answer for a 4th point. So this method doesn't work. It's not an easy thing to prove, but it turns out that there's always only finitely many rational points on curves of, well, on smooth curves of degree at least 4, I should say. There's this geometrical condition, which is basically saying there's no sort of pointy bits in the graph. If there is, you have to understand them by slightly different processes, because you might do things like drawing lines through the pointy bit of the graph and would get extra things out of doing that. So this is one of the major results of sort of the late 20th century mathematics, that there are only finitely many points on smooth curves of degree at least 4. That's all I have. So thanks very much.
Yeah, actually wanted to ask if you could elaborate somehow why indeed we have this few finitely many points and something which is smooth. Because it seems sort of arbitrary that we have something which is smooth and quite generally defined, and we are limited by a number of 16.
Oh, the in the finite part. Yeah.
Like this one is solved.
Yeah, I see. I don't really know for good reason. How you go about proving it actually comes down to studying these equations of higher degree. If you try and describe, so I guess you exploit the group structure. If you've got a finite thing here, that means that within the group structure, you can multiply it by the size of that finite group and get 0. So this is Lagrange's theorem for finite groups. And that gives you a new equation telling you what does it mean that I multiply this point by some n and get 0. And it's from the study of those higher degree equations that we can prove this fact that there's actually a bound on the possible degrees.
It's sort of embedded in the multiplication tables of the group we consider. In the sense that if you interpret the elements as geometrical objects, they will have some structure to them.
Yes. Yeah. And I guess another way to think about it perhaps is that these equations that you're solving say, what does it mean to be an element that you multiply it by 2 in the group and you get 0? That will look like solving a equation of degree 2, more or less.
Yeah.
Then it looked like solving equations of degree 3, equations of degree 4. So it becomes harder and harder for them to have rational solutions.
Okay, thank you.
Please could you re-explain what the rank means in this context?
Oh yeah, okay. So we had this theorem that we had an abelian group, and the theorem tells us that it has to look like something of this form, a product of a z to the r with a finite group. We're going to ignore the finite part, and we're going to say the rank is this number that appears in the z to the r. So the idea is, pretend there was no finite group here. Pretend it was just a z to the r. What that means is you can take r points, which are sort of the standard basis elements of z to the r, and those will generate everything by some combinations of those points in the group will make everything. So this r basically tells us how many points do I need to generate the entire curve. If I translate that into geometry, instead of thinking about groups, it would be how many points can I start with? And by doing the drawing lines process, combined with reflecting in the axis, can I get to everything? Everything, all the rational points.
So it has to be linear transformation.
So if you think of them, these are two groups that look quite different. The rational points on an elliptic curve and the z to the r, there's an isomorphism between them in the sense that there's a way that you can map all the points on the curve to points of z to the r and vice versa. But it doesn't look like any sort of ordinary map one right down. In one case, the group operation is just you add up sectors. On the other side, the group operation has this complicated geometric description. So it's not sort of an easy thing to write down the translation between. Perhaps I could say that's sort of fundamental. You may have heard of elliptic curve cryptography. So one place that the elliptic curves get used is in cryptography. That's not quite the elliptic curves I've been talking about here. That's using elliptic curves over finite fields. So roughly speaking, elliptic curves, instead of looking over rational numbers, we do everything modulo n, modulo p for a prime number p. And the benefit of doing that is you end up with everything being finite. But it's sort of essential to the way that the cryptography works. You don't want things to be too easy if you're doing cryptography. Well, you need problems that sort of you can do easily if you know some secret information. But if you don't know that, nobody can do it easily. So if you work with a group like Z to the R, everything's easy. You just have vectors, you do calculations, you know how to work with matrices and do those calculations. On the other hand, if you work in an elliptic curve, it might be abstractly the same group as Z to the R, but you've described it in a very different way, which means that doing sort of complex calculations in it is much harder. So we have a process that tells us how do we add points, but doing anything more sophisticated like, is this point a multiple of that one? becomes much, much harder because it's described in a sort of twisted up way. And that's essential to being able to use it to cryptography.
So what I got is that basically that arc rank is sort of the dimension of the basis, like
Right.
Yeah. But I guess there must also be some notion of independence between the codes, because for example, if we go back to our example before, we had 3 points, but that 3 points don't really count as a They can be in the same base. Right?
Yeah.
So my question is there a way just by looking at 2 points to tell if they are independent or not?
Yes, but it's harder than sort of, it's a reasonably complicated process. So there is a process, but it's complicated.
So there is an algorithm.
Yes. That's how we actually, you need that if you want to get these lower bounds on ranks. So if you want to say the rank of this curve is greater than or equal to 28, you need to find 28 points and then have a way to prove that those 28 points are independent. And we can do that.
So all these things apply to elliptic curves. not
Yes.
the other kinds of things.
Yes. Yeah, none of this sort of, if you go to higher degrees, as I say, the process just doesn't work, that you draw a line through 2 points. You don't get another one. So there's sort of nothing, there's no group operation.
So because elliptic curves pop up in multiple fields of mathematics, just elliptic operators and other stuff. So
Right.
this is sort of the fact that they have some kind of underlying algebraic structure, as opposed to other say conics or other curves in general.
Yeah. I don't know if elliptic operators are actually connected to elliptic curves or not. They might be, but it's also possible that sort of historically, sort of the they came up.
Perhaps like bounded mass, that they tend to circulate not to go to.
Yeah, it's possible.
The thing about the line,
Yeah.
circle, can be extended to more dimensions as in like x, y, z, and a constant. Two doesn't constant. So it'll be like a line.
Yeah.
So with like two, you can take Q and R as two of the gradients, and it'll be rational, and then you can generate I don't know, Pythagorean quadruplets.
Okay. Yeah. There's definitely things you can do in more dimensions. It starts to get more complicated. You have to decide things like, if you draw a line, so if say we work in 3 dimensions, and you're going to draw a line through it, if you take 2 lines in 3 dimensions, they probably don't intersect anyway.
As in like just here.
Yeah.
So
Oh, I see.
yeah, and then we fix a point.
Yeah.
And we have a line, and it goes around, and we define the partial derivative with respect to each axis. So there's 2 gradients.
Yeah.
And as long as the gradients are rational, then we will always have a rational solution.
Yeah.
X, Y, and Z. X, Y, and Z.
Yeah, I think I believe that. Yeah. Okay. Yeah, that sounds right. So yeah, I didn't actually know that, but this does sound right, that you can get rational points on a sphere.
Like a single line, you could perhaps reduce it to the case of the circle by taking the 2 points of intersection and projecting over or cutting off all the remaining sphere, so that we have like this.
Yeah.
And the orientation and all remaining dimensions will be somehow arbitrary because of that. Because we could shift the origin or rotate the axis so that we have our circle as the main problem and all the other space in rational. So
I see. Yeah. So yeah, I think that is intersecting with a lot of planes. Yeah, that's nice. I know there's things that one can do a little bit with surfaces of degree 3. Sort of to say a similar trick would work. If you have 2 points, you can find a third by drawing a line through them. But it's no longer a group operation, and there's no longer sort of such as rich in theory behind it.
I think that's it.
Thank you.
Thank you. Consent.